Let's take a look now at example number 8 and kind of return to an idea that we talked about near the beginning of this section, which is how do I show that a function is going to be continuous at a point, and how can I show that it's continuous on an interval? We've kind of looked at those two ideas previously, and we're going to kind of combine them here into a question like example number 8. This question is going to say, find a value of c. So c here is going to be a constant. You can see it down here in this function formula. And I want to find a value of c that makes g continuous on the entire interval negative infinity to infinity. That is, I want to make this thing continuous everywhere. Well, if I try to think about how I'm going to do this, I can kind of think about breaking this apart into a couple different pieces. First off, I can recognize here that in my piecewise function, I have at least a potential break in the graph occurring at the value of 1. And on one side of it, I'm going to get my blue portion. And on the other side of it, I'm going to get my red portion. Now, I don't know if, again, this is what the graph looks like, but there is a potential break. And what instead I'd like to have happen is for this kind of red hole to kind of perfectly go around that blue dot so the graph stays connected. That's what I'd like to have happen, right? That would be the ideal. I don't know if that can happen, but that's what we're shooting for. Now, what I have to go ahead and try to do then is to think about the following. If I want to show, though, that this is continuous, I have to write out a full argument. Let's see how I'm going to write this, and you would have to write something similar. First off, I would need to make sure that this blue portion of the graph, just the blue portion itself, is actually continuous. Because if I only connect these two spots and the rest of this isn't continuous, then the whole graph isn't continuous on the interval. So I'll start by noting the following. So I'll say, we know that g of x is continuous on, let's see, negative infinity up to 1. I can't include 1 because I'd have to say continuous from the right at that point. And I'm just saying regular continuous. So that's from both directions. So we know that if I'm looking at g of x and the blue portion, that blue portion's continuous. And the reason I know that is because x plus 1 is a polynomial, right? And that polynomial is defined on negative infinity to 1, and so it's continuous. Remember, that's what one of the previous theorems actually mentioned up here. Polynomial functions are continuous at every number they are defined at. So this is great. My polynomial there is continuous. So I know from negative infinity to 1, this blue portion is good. Now in the same way, I can say that we know that g of x is continuous on the interval from 1 to infinity, and that's because e to the 1 minus x plus a constant c is the sum of an exponential function and a polynomial. Now, the weird part here is sometimes for people is the polynomial. Remember that a constant is actually the same thing as a polynomial. It just has an x raised to the 0th power right after it. So this is considered a polynomial. And we know that this exponential function here is always defined. There's no problems with it, right? 1 minus x is always going to be defined. E to a power is always defined. And if I add on a c, that doesn't create an issue either. And so what we can see is that both of these functions, polynomial and exponentials, are continuous everywhere they're defined. And if I add two continuous things together, I get something continuous. So I can see then that there's only one spot in question. And I'll write down what we need. I'll say we need to find a value for c so that g of x is continuous at x equals 1. And in order to show that, we need the limit of g of x as x approaches 1 to be equal to g of 1. Now, we can see again, right, that we've already shown that it's continuous everywhere up to 1 and everywhere after 1, so 1 really is the only point that's in question. So let's go ahead and take a look at each of these things, see if we can calculate them, and see what we come up with. Okay, so I'll start by saying that we note that if I wanted to just compute g of 1, notice that would require that I use the top blue piece of my function. That's just going to be 1 plus 1, which is 2. So in order for this function to be continuous, I would need my limit to also be 2. All right, so I can go ahead and start checking the limit from both sides. My limit as x approaches 1 from the left, notice that's going to actually use my blue portion of the graph. And so that's going to use x plus 1. That's a polynomial, so I can direct substitute. 1 plus 1, that's 2. Okay, so far this is great. Let's see what the limit is, though, as I approach 1 from the right. Notice if I'm approaching 1 from the right, that's going to use the red portion of the function. And so I'm going to need to use e to the 1 minus x plus c in here. Now again, I can go ahead and actually use a really, really important idea here. Is this function here going to be, sorry, I can use a limit law, which would allow me to say that I'm going to be doing the limit of the first piece and then a limit of the next piece. And I'll just write out that I know that the limit of that next piece already is just going to be c, right? So I'll just kind of shortcut that. So I need the limit of this first piece. But here's something that's really interesting. Don't I already know that this piece is a continuous function? If this is a continuous function, then by the definition of continuity, this would be the same as just its y value at the point. So what I actually can do is simply, again, just plug in the value of 1. Notice this is going to get me e to the 0, and so this is going to get me 1 plus c. Now, here's the issue. I can see right now that I want to go ahead and make the function g continuous at the value 1. That is, I need the limit and the y value to match. The y value is 2. The limit from the left is 2. What would I need the limit from the right to turn into so the limit can match the y value? Well, I would need it to also be 2. So I could write something like this. If c is equal to the number 1, then the limit as x approaches 1 from the right of g of x would be equal to 2, and thus the limit as x approaches 1 from both sides would be equal to 2. And that would make the limit and the y value the same. So then I could state that if c was equal to 1, then the limit as x approaches 1 of g of x would be equal to g of 1, and g of x would be continuous at x equals 1. But if g of x is continuous at 1, and it's continuous everywhere before 1, and it's continuous everywhere after 1, then clearly I can state that g of x is continuous on negative infinity to infinity. That is a rather complicated argument. And again, please notice how many words I've had to use to kind of describe what I'm doing. Don't shy away from that. It's extremely important. So this is kind of a really interesting kind of collection of all the different ideas that we've discussed. You may have to go back and re-watch this video maybe a couple times to get the hang of what exactly we were doing here. But of course, there are also a large variety of questions like this in the worksheet. And that's very important because there are questions that are also going to be like this in the homework. So make sure that you go back, take some time to review questions like this to really think about what exactly we're arguing and why it makes sense. And of course, if you have any questions, please let me know.